All right, number 6. Functions f, g, and h are twice differentiable with g of x is equal to h, or sorry, g of 2 equal to h of 2 is equal to 4. So both of them have the 0.24 on them. The line y equals 4 plus 2/3 x minus 2 is tangent to both the graph of g and the graph of h at x equals 2. So that's the tangent line to both of them. So find h prime of 2. This is the slope of h at 2. We look at the tangent line. What's the slope of that? It's 2/3. So a is 2/3. B. Let a be the function given by a of x equals 3x squared h of x. Write an expression for a prime of x. Find a prime of 2. Okay, we're going to need the product rule here. So essentially a of x is 3x cubed times h of x. And that's how we want to think of it in terms of the product rule. So a of x equals 3x cubed times h of x. So a prime will be 3x cubed times h prime plus 9x squared times h. Then a prime of 2 will be 3 times 8 times h prime of 2, that's what we found in a, 2/3, plus 9 times 4, h of x, this was given to us in the stem of the problem, h of 2 is equal to 4. And then this is whatever that is, 160, because I'm looking at the answer key. Part C. The function h satisfies h of x equals x squared minus 4 over 1 minus f of x cubed, for x is not equal to 2. It is known that the limit as x approaches 2 of h of x can be evaluated using L'Hopital's rule. Use the limit as x equals 2 of h of x to find f of 2 and f prime of 2. Show the work that leads to your answers. Okay, so let's see now, where are we here? Okay, so h satisfies that for x is not equal to 2, but the limit as x approaches 2 of h of x can be evaluated using L'Hopital's rule. So we got a couple things going on here. We know that x squared minus 4, the limit as x approaches 2 of x squared minus x 4, 1 over f of x cubed is going to be equal to 4. And if we're evaluating it using L'Hopital's rule, we know x squared minus 4 is equal to 0, and 1 minus f of x cubed is equal to 0, or sorry, f of 2 cubed, 2 squared minus 4 is equal to 0. Okay, so right, we're using L'Hopital's rule in the case where we end up with 0 divided by 0. And so if we evaluate those limits, basically, right, this is when we can use L'Hopital's rule, when we're getting a 0 over 0. So both of those are true. This one obviously is true. 2 squared minus 4 is equal to 0. So this one must also be true. So 1 minus f of 2 cubed is equal to 0. So f of 2 is going to be equal to 1, basically. The second thing is that L'Hopital's rule is when I take the derivative of this over the derivative of that, that's when I actually get 4. So the derivative over the derivative is equal to 4. And so let's find these derivatives. The derivative of this is going to be 2x. The derivative of this will be negative 3 f of x squared times f prime of x. If I can evaluate this one by plugging it in, I'll plug in 2, I'll get 4. Whoops, let's just actually plug that in. So 4 over negative 3 f of 2 squared f prime of 2 is equal to 4. We know what f of 2 is from up here. So we have 4 over negative 3 times 1 squared times f prime of 2. And let's see now, what do we want to do? Multiply by f prime of 2 divided by 4? Sure. Fours, leave the 1. Negative 1/3 is f prime of 2. That one is quite convoluted, I won't lie. But yeah. Okay, part D. It is known that g of x is less than or equal to h of x between 1 and 3. Let k be a function between g of x and h of x between 1 and 3. Is k continuous at x equals 2? Alright, continuity at a point. The limit needs to be equal to the value of the function. So, we have a couple things. We know that both at 2, g and h are both equal to 4. So, let's start off with the value of k of 2 is going to be equal to 4. So D since g of 2 is less than or equal to k of 2 is less than or equal to h of 2 is equal to 4. We'll put 4 on both ends. Then k of 2 is equal to 4. Now, all we have to do is show that the limit as x approaches 2 is equal to 4. Alright. Since g of x is less than or equal to k of x is less than or equal to h of x, by the squeeze theorem, the limit will be the same. And now, since my limit and my value are the same, since k of 2 equals the limit as x approaches 2 of k. K is continuous at x equals 2.